So, hi students, welcome to another very exciting session of healthcare entrepreneurship. We are going to pick it up from where we left last time. So, let us get started. Over 10 million plus engineers, 10 million, we are looking at 1 crore close to of engineers and designers at more than 565,000 companies were using this software as of 2022. So, as far as 2022 latest statistics is concerned, all these 5 softwares were together used by so many populations. So, you could imagine that what is the major market share of the software. So, these are the major players. If you look up online, you can find tens and hundreds of other softwares which will let you design something online or let you download it. Many of the softwares are not very well validated. So, these are the popular ones. But with the popularity, another thing which really comes is the cost. So, SolidWorks, I think licenses are fairly expensive, like and the other softwares similarly follow the line. So, unless and until you are a student at a very reputed university or you have some funding from for some research to support these kind of softwares, it would be a little difficult to kind of get hold and actually run this softwares, the full versions of it, right. It is typically recommended to not use the pirated versions and other versions of the softwares, because that kind of breaks the sanctity of research and the entrepreneurial circle, right. So, it is used to make advanced 3D model design, all the softwares which are typically known as CAD, which is computer aided design, that is what it stands for, assembly of parts. So, you can create different parts and then further create an assembly. Can you create an assembly directly? In few cases, yes, if there are no moving parts or parts which require some kind of relative motion, then you can create an assembly of parts within a single part. But in majority of the cases, you will have separate parts which are assembled together using a different function which is known as assembly function, right. Then you have analysis, which is using CAE, which is computer aided basically analysis and engineering. Then you have 2D drawings and additive manufacturing simulations, etc., which are typically used for understanding and kind of implementing these drawings and models into an additive manufacturing simulation kind of setting. And you can 3D print most of these files directly off of any of the software. So, that is also very, very handy. Okay. So, oops, there's a slight glitch. So, just continue here. All right. So, the next part is we would like to look at some of the design tool based applications. So, the first application here is the implants, right. So, you can create a lot of different implant designs based on the existing dimensions as per certain standards, or you could come up with some new tweaks and turns based on some innovation or clinical expertise. You're looking at a typical hip implant on the very left, and I've just introduced it. You will be very surprised to believe that there are at least 50 to 100 variants of such hip implants, not only as per age and size of the body, but across different directions in which this research in hip implants have occurred over the year. In terms of surface modification, certain implants it's a little more tapered, there are cemented, uncemented implants, there are implants which have like certain screw like threaded structure in order to enhance the bone growth. There are so many aspects to the design which several groups in collaboration with clinicians and doctors have come up with here over time. So, even though while you're talking about designing of an hip implant, you have to be careful of that literature and what exactly the dimensions, how have they evolved over time. So, that kind of a detailing is needed if you're looking for innovation in this sector, right. Next is a typical spinal implant. So, if there is a spinal injury which has caused some kind of deformity in the different vertebrae or discs, as well as there are cases in which some of it can be from the birth and some of it due to the profession which you are having, like where you have a lot of load bearing component, you're lifting weights and whatnot, or it happens very often to mothers who have been bearing a lot of load to during their pregnancy years, and basically then the child is there and they're constantly carrying them. So this deformity is known as scoliosis. So if you look up scoliosis, you will see a numerous amount of research have gone into the spinal deformity, which basically causes as an effect like a bend in your spine. There is a kind of a temporary ranging from the temporary to a permanent bend, which is typically solved by using some kind of a spine based implant or spine spacers, or sometimes you have certain like orthotics which are put along in order to prevent that. And there are a number of other spinal deformities which requires these kind of spine implants to make sure the vertebrae and discs are held in the right place, right. So then there are elbow implants and knee implants which are also kind of designed in this using this design softwares and tools. Next application is assistive devices. So the first here is a very interesting one, which is known as an exoskeleton. So many of us, like in the engineering domain, may have heard of what an exoskeleton is, and for many of us this may look like something right out of the movie Terminator, or like from somewhere in the future, like the Star Wars or something like that, So typically what this exoskeleton does is it can be this whole body exoskeleton, as well as this could be an upper body or lower body exoskeleton. So this is typically kind of a medical device only, medical wearable device, which is built for patients who have lost their limb function to some certain extents. So there have been cases where somebody has met with an accident, or there was a fall, or somebody served as a part of the military and probably got injured pretty badly, and they've lost their limb function. Basically, it could be upper limb or lower limb. So exoskeletons basically provide an electronic way as a upper covering. So it doesn't replaces your lost limb or dysfunctional limb. It basically goes as a cover, kind of as an orthosis, which is a covering for this, and has electronic components such as motors and actuators and sensors and whatnot. So basically what that does is it gives you that extra push to get your foot up, or walk in the perfect manner. And you could have controls. If your foot is completely damaged, then you can have a full force exoskeleton which is letting you walk normally using all these different activities or steps which it performs, very similar to a human walking. As well as there are cases where you don't have enough sense on your foot, but you can still feel your foot and maybe do a few light activities. There the exoskeleton will give you that extra edge, that extra push to add the additional force for walking or doing the daily activities normally. Similar with the upper limb, and there are cases where there are lower to full body paralysis. That is again where exoskeletons really serve a huge purpose. So there is a huge thirst on exoskeletons worldwide right now. So a lot of the labs and companies are trying to jump on the bandwagon basically, and a lot of you folks in the startups can also explore this area, in the area of prosthetics and orthotics, where this have to be a little bit cost effective. That's what I've felt from my interactions with doctors and the stakeholders in this specific domain of exoskeletons. So it has to be cost effective in the sense, right now if you're looking at several companies abroad are doing this, but it is super expensive, very high quality of course, because this is a lot of gate based activities which are performed. As well as you have several other functionalities, constant dynamic measurement. It keeps on measuring the loads which are applied if you're able to do it normally, have AI and other adaptive techniques, but the prices are usually on the higher side. So if that can be reduced through some Make in India initiatives, that would be really encouraged, right. The next example is a smaller version of the exoskeleton itself, which is like a hand based orthosis. So this can have different modalities, like it could be a hand based orthosis which helps you to mechanically do a few things, or could have an electronic actuator which basically helps you do certain things. And the third part which can happen is basically where you have some form of control with the brain, or it could be a control along with some kind of other muscle activity monitoring, which gives you a feedback based control. So there are so many aspects which are kind of introduced these days into the research in hand orthosis. But the end goal is very clear. If you have lost some level of functioning on your upper limb, which is the hand in this case, it is trying to aid that and let you do the normal functioning. So this is sometimes also used for rehabilitation for people who have faced certain amount of trauma and they want to rehabilitate in order to get to that normal form. So this can be used for a certain amount of time and then kind of left behind, and while you have kind of regained your consciousness completely and you're totally able to operate normally without the orthosis, right? So these are some examples of assistive devices which are also can be designed in multiple parts and assembled together. Some other examples is a wrist orthosis here. This is something which was developed as a part of my lab in IIT Delhi. So we have come up with a mechanical version of it, so it doesn't have any electronic components so far. So this is typically for patients with spinal cord injury where they have certain issues with their daily activities where they are not able to grasp certain objects and able to do their daily routine activities such as brushing or eating or writing. These kind of activities are difficult for them. So typically what this orthosis has is it's a hinged bicep brace. So basically it fits on the biceps where they still have a good amount of strength left, and there is an elbow joint from which basically the strength has actually gone down for this particular person. Then there is this gear casing, worm wheel and worm gear. So there are a lot of nice mechanical gear based assemblies, and there is a turn knob. So if you have full functionality in one of your hands and the other hand is kind of gone through some trauma, it's not able to perform normally. So typically what you do is you turn the knob using the other hand, and that is going to put your arm or your basically fingers in the right direction where you can hold a spoon or do your brushing activity and whatnot. So there are some knobs for tightening some daily use items, like there are knobs for holding the items properly as well, right? So there are so many aspects which can be done here while your fingers are also not moving. You could just have the spoon and kind of use it like this, right, where the spoon is kind of tightened to it. So this is another wrist orthosis totally developed on SolidWorks. So all the dimensions were captured from the basic human body. So typically when we are trying to make a device like a prosthetic and orthotic or a wearable device for a generic population, we would like to see at the 95 percentile human dimensions or 90 percentile human dimensions. Like what that means is these dimensions will suffice or be just okay for 95% of the human population, irrespective of their weight, height or whatever. So it's like a one size fits all kind of system, right? But there are cases where very custom orthotics or custom systems have to be built, and that is on a case by case basis, right? So this one was built around a generic human dimensions, like of what the arm length would be, and it had some adjustability, like just in case somebody had a longer arm versus a broader arm and whatnot, right? So those details were all factored in, and this is one of the wrist orthosis completely developed in SolidWorks. And what you're looking at is a complete design. Actually, this is not even a picture outside. So even the hand design was kind of loaded from somewhere on SolidWorks and basically done through 3D scanning, which I'm going to explain in the upcoming slides. And this entire design was such a nicely integrated. So if we basically try to pitch this to certain folks, and then they will have a very easy understanding of what this device is, right, rather than we trying to speak about it or just talk about it. So some of the technical designs we would like it to be presented rather than being in the very early stages of just knowing the value propositions or just knowing the terms and terminologies. So that is something which is encouraged for all the folks working with medical products as well. The next thing is wheelchair designing. So we have seen so many different variants of wheelchair. It doesn't only differ from hospital to hospital, but it differs from one state to another, and you could see quite a few differences across countries. So my experience with traveling to several countries have been the wheelchairs look completely different. The functionality or the need is the same, but there are so many add-ons and other features along with it. In several places you have electronic wheelchairs, and majority of the places you still have them mechanical. There are certain aspects to the wheelchair design, such as what should be the lengths, different lengths for right comfort, so that the patient who has maybe just come out of a trauma or a surgery can be carried in the best of the comfort and doesn't incur any other injuries, right. So typically a wheelchair design has evolved over time, and you would still see so many publications and works and groups working on this wheelchair design, trying to make this more efficient, more portable, and something which can be put on the side, and something which doesn't have wheels, which have in cases like when they're going from one terrain to another, they're not locking in or giving a jerk to the patient, right. So many times what happens is, while you're carrying a patient in a wheelchair and you're going through this different ramps, and there's a smooth terrain versus you're going through some rocks or some little bit bumpy terrain, all of a sudden the front wheels will lock and there is a sudden jerk. This is something you would not like to happen to a patient who has just been surgically operated, right. He has some stitches which could be breaking or getting affected, like if the wheelchairs have this jerks. So many a times you will see shock absorbers placed along with wheelchairs, which will take away that jerk, right. So so many aspects of this wheelchair designing are still going on, and majority of the softwares used are like SolidWorks or CATIA specifically. Some other applications include the wearable design, where the first one you are looking at the kind of GUI or the graphic user interface for the SolidWorks, and you are basically looking at designing of a hearing aid. So they are trying to design a hearing aid with some features which are maybe better than the existing ones. The second one is a smart glass, or a smart pair of glasses, which basically has several electronic features and viewable features along with it. And this is also designed in this kind of a SolidWorks kind of framework, right, in parts of course. The third is a smartwatch, which is very similar to the example we had been taking for a while, which is the project on Halo smartwatch. So smartwatch also has several components, from the band to the different components of the screen and the covering and so forth. So all these components can be designed within a system and assembled to look at the initial designs and kind of iterate from there, right. Some other applications include the prosthetics. For example, you have this lower limb based prosthetic, which is one of the most classic prosthetic you would ever see if you search for the term prosthetics. So that's typically when somebody loses the lower limb, and it is prosthetic is a little different from orthotic, as I've explained before. Prosthetic is something which completely replaces the limb, right. It doesn't aid or goes as a covering on the limb, which is in the case of an orthosis, but prosthetic completely replaces the structure and the functioning of the limb, right. So this lower limb, if it is completely replaced by a prosthetic, then you would like it to be able to be comfortably integrating with your body, as well as you want it to bear the right amount of loads and have the right pressure distribution, so that all of a sudden, while you're trying to walk or adapt yourself after introduction of this prosthetic, you're not falling down because of a load mismatch or some disbalance, right. So lot of these effects have to be looked into while designing a lower limb prosthesis. So while you do this lower limb prosthesis, there are just so many designs out there in the market again, with shock absorbers. You have multiple components which all of a sudden, if you hit a mark that there is an impact, it can take away that amount of impact. Then it can have nice liners made up of silicons and other materials, like which are comfortable to wear, right. And overall, from a functionality standpoint, you want it to bear the load rightly and have the right balance, right. So there are a lot of lower limb designs which are out there in the market. Which one is good or bad, that is open for discussion, but there are so many advantages which have basically caused this area to explode over time and have a lot of innovation. And the recent ones have a lot of electronic sensors, components along with it. So all of this is designed in SolidWorks, or this kind of a CATIA kind of setting, right. Another example of an upper limb prosthesis, very complex. You're looking at a complete replacement of the upper limb kind of work. So basically, of so many joints, and every joint there might be some small motors and actuators to kind of have all the different motions of your arm, like this twisting motion, there is this finger motion, and there are motions like this, and that. So many motions like which have to be operatable or implementable through your design. So this becomes another form of design. There are designs which do not, where nothing really moves around, and there are designs and assemblies where there are so many moving components. You have to be more careful of designs like this, which has a lot of moving components. So just make a wild guess on how much time it may have taken to complete this design. So if you would spend like a few seconds to just appreciate how complex the designs are and so many joints and functionalities this particular design has. Requires a lot of planning, requires a lot of understanding of the particular standards, and also what exactly should be the dimensions of the different components of the human body, and if this could be made generic like an 95th percentile human, something like that, right. So that is typically the norm. Let's go further. So some of the 3D scanning technologies are the new age technologies where you do not need to hand design from the scratch. So majority of the medical implants and devices earlier used to be all designed from scratch, from a simple sketch of a circle, and that circle is extruded in order to get a cylinder. That cylinder, there is a sketch on top of it, there is a extrusion or another cylinder coming out of it at 30-degree angles and so forth. So these kind of detailing used to be done like from the scratch. But these days what has happened is there are technologies known as 3D scanners which can just scan the entire model and can quickly give you a CAD design. There are a lot of shortcomings to that aspect, but it still saves a lot of your work. Basically, while a designer is spending 100 hours to trying to design a particular implant, you can just quickly take the scan of this implant within probably a few minutes, and that's it, right. You should be able to make this design. So this 3D scanning technology is something very new age, which many of you can consider. So this is one of the applications from the 3D scanning technology which we have implemented in our lab setting. So what we did here was we basically took a subject's foot. This is one of my students, and we basically use this 3D sense scanner. This is from 3D Systems, I believe, and this scanner is fairly priced. It's around 50 or 60,000 rupees, and not a super high quality, but okay quality to just get it right. And in the computer, we are basically looking at the scan. So the scanning needs some form of skill sets, like you need to be able to scan it right, hold it right, or move it right. So those things are very important. It's not like I just take the scanner and move it 5 times, the scan is done. No, it's not that easy. But it does have a certain learning curve, but like it is still easy to learn. Somebody who has tried it 4 or 5 times and failed will be able to quickly do it, right. So if you are stably able to like move the scanner around for a while, you would be seeing the entire foot model, the 3D model, show up on the screen of your computer, which you can rotate or pan zoom or do anything with it, right. So this makes life very easy, where your entire foot model can be traced within maybe 15 to 20 minutes, right. And there are places in which you will see the model is not developed, there are some vacant spots and cavities. That is where you can move your scanner around a little bit more, and it will scan that part as well. It will complete that system, right. So having said that, then the next part is based on this foot model, we wanted to develop customized insoles. So that was our end goal, using the scans. So sometimes one thing to notice is what you do scan is not always the end product. This is something to get out from there is, so we have scanned the foot here, but the end product which we are trying to build is not the foot or a foot model. We are trying to build an insole around it, right. So typically how would we make insole from a 3D scan? So the scanned model, if you can see on the figure on the right, So the first figure basically shows the scan model from the two different views, scan foot model. As you can see, the quality is not very detailed. A foot will not look exactly like this, but the outline is okay. It will at least give you the outline which is necessary in this case for defining the insoles, but it is not super detailed, right? In certain aspects or certain applications, you may need the exact details to build a custom insole or custom something, but for a generic insole or even for custom insole, it suffices to have the outline. Typically how this is done is you place your foot into something which is known as a biofoam. It kind of goes in, you put plaster of Paris and you get a model out, right? That's typically how this is done. If you go to any podiatrist or pedorthist for formation or making your custom insoles. But in this particular case, for the scan model, it is much more easier, much more cost effective, and much more time effective for that reason. So next what you do is basically you place the scan model within a 3D modeling software like SolidWorks, and basically create a mold design around it. This mold design would be used for further casting of the different components of the insole, right? So you can easily trace using some offset operations, like with a slight gap on the foot, kind of trace the mold of the half of the foot or 70% of the foot, what we did in this case. And we 3D printed this model of the mold, which is a PLA based polylactic acid. This is a common standard filament for 3D printing. This was printed out, and we use this mold to cast a polyurethane or PU based base. So we poured some compositions of polyurethane and got something out of it, right? Then we took a Evazot as one of the base insole materials, and we cut it out in form of a certain size of foot or size of insole. So there are standard foot sizes and standard insole sizes which are out there in the market. So we kind of cut it out in that form, and then we cut out the insole in certain places where usually a person would encounter very high pressures. Typically the high pressure zones are the heel of the foot, and another zone is the ball of the foot or the near to the toe region, right? Near about to the metatarsals specifically. Metatarsals are the ones which connect with the end of your toes, right? So these are the two cutout places where further silicone was poured, and the final insole basically had this 3 or 4 components. So this had the cutout standard insole material. Then you had 2 pourings there, basically much more softer materials at the locations where you would usually encounter high pressures. This is to offset or dissipate that pressure. And then you have the final insole arch, which was built out of the PU. So all this jazz of doing the scan model and PLA mold and the casted PU base was just to look at the contour of the arch. So as we all know, we have very different arches going from one person to another. It's very customized, it's very personalized. So some people have flat feet condition where the arch is completely collapsed and they have a certain way of walking, and it could be also gauged from the direction in which their shoe basically gets worn out. So if somebody walks for 6 months on a shoe, you would typically find out, you can find out what kind of arch size they have just by looking at the bottom of their shoe. So typically what happens in my shoe is it gets worn out from a certain direction. So I know I have some kind of a flat foot condition, right? Then you have a normal arch where you will not see a lot of shoe wearing, and then you have high arch where foot kind of bends in the other direction. So they are typically known by the term supination or pronation, right, due to which you see different varieties of arch affecting the overall gait in a different way. So we wanted an arch support, which is a strong arch support, and this finally builds your product, right? The product here is this multi-material customized insole, right? So things to note here is we designed something else and we got something else for the product. The next application is dental application, where you could do some kind of a 3D scanning of the teeth using some form of intraoral scanners. There are specific scanners which are like 3D scanners only, but you can look inside the teeth and get an entire model of the teeth. or there are single tooth models which can be taken through something which is known as a CBCT scanner. It's form of a CT scan, but which has this CB component to it, so it's a CBCT scanner, right. So these scanners are often used to develop the 3D model of the entire teeth or a set of teeth. So then you finally have a 3D printed model using different formulations of the material which you may like, and you use this 3D printed material model where you are looking at some supports. So all the lines here, basically you are looking at supports, because 3D printing cannot happen in the air, so that kind of creates a support whenever you have something hanging, right. So you remove the supports fairly easy, and then you finally get the model. So this was one of the dental application, and you could use this models for doing a lot of surgical training, or for defining some kind of a cosmetic surgery, or for planning a crown root kind of treatment, or some kind of a fracture based treatment where there is a tooth reattachment, dental trauma, whatnot. So many things are used for from a research standpoint, and many a times to cast a new tooth, right, tooth implant. So the next is design of prosthesis. So many a times the 3D scanning is used for looking at the area of the lost limb. So this particular person, you're looking at the figure on the very left. So this particular person has lost a limb, and he has a particular arch and contour of that location where from up to which he has lost his limb, right. So someone may have lost their limb like from a much more lower region, and someone may have lost their limb from the much more upper region. So for this person specifically, who has either got an amputation or has lost the limb completely, the scanning of this particular region becomes very important to design the cup which goes inside the lower prosthesis, right. We are looking at the second figure here, where this is a total prosthesis, right. So the designing here, design component is basically the cup, which is the brown part, or the which is going inside here. Rest of the model can be off the shelf. So that basically saves us a lot of money if you are part of an entrepreneurial venture like this, where you can just design the cup which is customized to make sure it's of high comfort and nice fit to all the patients, and basically you can use 3D scanning and 3D printing to do that, and then finally fix it within an off the shelf kind of prosthesis, and this saves you a lot of money. If you were to develop this entire prosthesis from scratch, that's a lot of designing, lot of product development, lot of components, right. So this is again another big innovation with the design, that you could design something custom specific, and usually it is difficult to take the hand drawn measurements from that person, so scanning might suffice, right. One place where scanning doesn't do very well, and I'm going to talk about it more, is scanning cannot scan the internal components of any design. This is a point to be noted. It can only get the peripheral or the outer designs, right. Then the final step after the scan model for this cup designing is basically the production of the cups, and which goes in straight into the off the shelf model, right. So this is another example of design of prosthesis. Another example is design of standard of care. These are commonly known as standard of care insoles for diabetic foot management and arch measurements for the same. So the first example which you're looking at the very left is basically a person is standing on a foot scanner or a foot bed, where they're trying to get like this basic impression, and basically based on their impression there is this particular model which can typically be taken very easily through a 3D scanning, and around that 3D scan model you can basically place an insole within this SolidWorks or some kind of a software tool within itself, right. And you can just directly print that insole which you have fitted or done a simulation fit within the software, right. So you do not need to now go to that person 5 times to check, or have that person sit with a plaster of Paris cast or something like that to or mold the insole around his foot or something like that. So those things can be totally avoided. So this creates a lot of innovation into the prosthetics and orthosis space, where you can quickly 3D scan certain things, modify it a little bit within your software, and basically create medical devices, wearable technologies around that particular model, right. Another example is the customized heel cup development. This is typically a lot of us have heel based problems, and this basically falls under the broad range of problems of plantar fasciitis. The plantar fasciitis is basically a generic problem of the plantar fascia. It's a specific tissue which basically connects from the metatarsal all the way up till the heel, basically some form of the heel. So that plantar fascia is kind of responsible for giving the arch shape to your foot, basically. So this is a very important the soft tissue underneath the foot. So typically with loading and unloading in athletes and people who walk a lot, the plantar fascia can get damaged, which would typically cause pain around the heel and sometimes on the metatarsals, right, the 2 points of connection, basically. So these basically difficult to maneuver or difficult to manage pains can sometimes be managed using orthosis. So you could have painkillers, but that would not create a long term solution. So the orthosis like heel cup will basically give you the right cushioning at the location of the heel and let you basically absorb the shock on the plantar fasciitis like going forward, or the plantar fascia going forward, and this relieves you of the foot pain quite a bit, right. Another example is the design of braces for the spine, right. So earlier I have seen one of these examples in during a scoliosis treatment orthosis which was built, got some hands on there. So typically what they do is they take a person and they kind of hang that person from two sides, like by putting some ropes kind of thing where their entire body weight is like sticking down, like basically going down. Then they kind of modify a person's posture like correctly so that the spine has taken almost a clear straight line kind of form, and then they put this plaster Paris kind of cast which is placed around, very not very painful, but it's kind of not very comfortable, like for somebody to stand for such long times, and then they finally create a brace around it. Now that can be done very easily by 3D scanning the body. Within no time, the person doesn't even have to stand around or do something for a very long time, and this person this particular brace can be fit around it very quickly, and this after this brace is fitted, like then further validation can work out, like that how this person is performing with this particular brace, or this needs certain level of adjustments. So this takes out a lot of manufacturing efforts, manpower efforts, a lot of designing efforts. So a lot of these details are completely taken away by this simple processes, innovative processes of 3D scanning and printing, right. Earlier traditionally also how they do it in several hospitals and clinics, that can totally be replaced if this is kind of placed in the right platform and you can give the right confidence that this scanning and printing is going to really be accurate. This will typically be much more accurate than the traditional version, where somebody may be prone to moving a little bit and the brace can completely shift. It may not be completely taking the load of a scoliotic patient, and there could be still a bend, right. But this 3D scanning will give the perfect posture and perfect shape, and that you can use to create the right brace. So this is another designing evolution or innovation where a lot of you folks can work on, and I've gained some personal experience with this as well, like where we have seen this area is completely open. Most of the top-notch clinics are also still using the traditional techniques where they have somebody who is putting them in all this through their methods and protocols and designing this manually. Very low, very heavy on time and cost, basically. So this is completely open to innovation if you are willing to work with few of this majorly physiotherapists, there are surgeons, there are doctors, specifically ortho based doctors who are working with these kind of aspects. So you can work with them to 3D scan and 3D print. This itself is an innovation where you can make custom braces, right. The next type of file I would like to talk about is based on medical imaging. So, basically DICOM is a very commonly known term. It is a terminology used for the type of file. Okay, it is a file type, like we have .jpg or .bmp or .png, like for any image file. DICOM is a very similar setting. It could be compared with something closer to a zip file. So, what DICOM typically does is, it stands for Digital Imaging and Communications in Medicine. It is a standard for the communication and management of medical imaging information and related data. DICOM is a very well known term across the industry wherever there is a medical imaging which is conducted, be it CT or MRI, right. Typically, there is a way in which all these machines are kind of having this add-on where all the stack of images which they have taken across the body. So, if somebody has been placed inside an MRI machine, then there are a lot of images which are taken at these slices and at certain intervals. All these images are kind of stacked together in form of this DICOM file. Acts similar to a zip file, but cannot be read by just double clicking on it. So, typically you need some kind of a DICOM viewer or DICOM viewing software in order to process these kind of files. There are a lot of DICOM files available online which you can download. They are part of the National Institutes of Health, which is NIH database, and there are visible human databases like there is a Korean male and Korean female database which I personally used for research, which you can use. You have to of course get the permissions and the right protocols done, but many of them are completely free to use. You can download these softwares, download the DICOM files and use any of the online DICOM viewers which are downloadable viewers as well, and run through these different stacks of the CT or MRI images of a person. Many of the set of images are not only from the normal normal healthy person, like there are cases, there are also from the case studies such as when there is a tumor growth going on in some person, or there is a certain kind of brain damage or some kind of a deformity or injury which has happened to some part of the heart or brain or the head trauma. So, these things are all captured. Even I have worked with the human pelvic system where there has certain deformities or fractures which are tracked through these kind of DICOM images. So, DICOM is most commonly used for storing and transmitting medical images, enabling the integration of medical imaging devices such as scanners, servers, workstations, printers, network hardware, picture archiving and communication system, which are the PSCS, for multiple manufacturers. So, what this basically means is DICOM is a very standalone file type which has gotten traction and gotten very popular for any kind of medical imaging modality. So, similar to if you are looking at any of these 3D scan based files, they are typically stored as .stl for which is a common 3D printable format, which is known as .stl or stereolithographic type of file, which just gives a surface profile of something, right. A similar DICOM basically has multiple pictures kind of stacked together, right. So, the next thing which you do is basically you have a DICOM viewer in which you can load a DICOM file, and this DICOM file basically stacks images in 3 planes. So, if you look at the human body, you have one plane here, one plane like this, and then one plane going like this, right. So, you have the sagittal plane, you have the transverse plane, and you have the coronal plane, which are basically the 3 planes which are part of the human body, quite widely known. You can look them up. And so, typically these DICOM images are loaded in a viewer in these 3 planes, okay. So, there are images in all these 3 planes and there is a window. So, let us take a look at the figure on the left. You are looking all these 3 planes images, which are the second, third and the fourth images from the left side from top to bottom. And then on the right side, you are looking at an entire model of the skull, kind of with some form of eye tumor or something which is there, which can be distinguished in color basically, right. So, in a DICOM viewer, you can basically move using your basic cursor of your mouse or through your keyboard the up and down cursor or sidewise cursors, like from one image to another, and there are stacks of, let's say, 200 images in the coronal plane, maybe 500 images in the transverse planes, and let's say 300 images in the sagittal plane. So these images, what we typically do as a next step is known as image segmentation, right? So image segmentation is a process I'll explain in the next slide, but that is typically how do we get a 3D model from this set of 2D images which are in 3 different planes. That is what image segmentation process usually does. There is another viewer here which is micro DICOM viewer. So Brain Labs viewer, if you just search online, you will see hundreds of these DICOM viewers. Lots of codes which are downloadable. Just be aware of, like, there could be few ones with viruses, so just look out for some of the popular ones. There are quite plenty of DICOM viewers which can be downloaded, and you can process your image through that, right? So DICOM viewer is just to view the different slides or different stacks of images which are there as a part of the DICOM file. The next thing which you do is basically within this DICOM image viewers, like you can see both MRI and CT images. All the imaging modalities, be it MRI, CT, or some other forms of imaging, typically is kind of focused towards either looking at the soft tissues or the bones specifically, or demarcate certain soft tissues by different colors and whatnot. And they use quite a bit of light thresholding techniques and whatnot, like for that. So in a DICOM viewer, typically when you look at a 2D slide, unless you have a clinical eye or a clinical view, it may be very difficult for somebody who has never seen a scan before to really demarcate which is what in terms of organ or tissues, right? So sometimes many of these DICOM viewers may help you to demarcate this organ specifically. So you can select this is for the kidney, and you load up this particular set of DICOM images, and all of a sudden it kind of demarcates this is this lateral side of the kidney, this is the longitudinal side, and this is some other portion. Some anatomical terms will come along, right? So these are some typical places in which DICOM viewers can look at. And there are these 3 planes in which basically what is happening is, next step is segmentation. So segmentation is where you are trying to create a contour around a particular type of soft tissue or bone or any kind of structure which you are trying to pinpoint towards and create a model about, right? So within this scan, if you can clearly have a demarcation that this region is a particular organ or a soft tissue which I want to model, then I keep on creating contours around this model in all the 3 planes, like wherever I can see that. So can I process this 200, 300 and 500 images all of a go? No, not really. So what you could do is do a segmentation, we call this contouring or segmentation, every 3 or 5 images, you know, wherever you see a huge shift in the kind of image, whatever you can see as per as that organ or particular location is concerned. So that is something which you can do, right? The next step is once you have started contouring it, this is known as a manual contouring. There are several softwares out there which can do a quick contouring within a few minutes. They have some AI based modalities and some other functionalities where whenever you put a set of DICOM images, they will quickly give you this is the femoral bone model, right, in no time. Most of the softwares are very, very expensive. So what we have done previously as a part of the research is we have looked at several image segmentation softwares which are free of cost. One of the good ones is TurtleSeg, you can look it up. Another one is ITK Snap. These are some free softwares, but usually you would spend, I had looked at the pelvic system, like defining several organs like the bladder, rectum and other organs around it. Typically took me around like 30 to 40 days to actually end up segmenting those, right? So if you are in the medical simulation market, or you are trying to look at certain organ based you know, models and prints as a part of your entrepreneurial journey, so it is a good advice to go for some auto image segmentation softwares and maybe create a budget for that. They are typically very expensive, but you would want to create a budget for that, right? Makes your life a lot easier. One example of this software is some of the auto segmentation software is Materialize Mimics. This is a very popular software. It is an image processing software for 3D designs and modeling, developed by Materialize NV. This is the company, it's a Belgian company specialized in additive manufacturing software and technology for medical, dental and additive manufacturing industries. So, this software I have had a hands-on knowledge working with it. So, typically what this does is you fit a set of DICOM images of the entire human body from let us say the MRI scans. Within just a few minutes it clearly gives you all the different bone models separately, several organ models separately, few of the very discrete tissues which are difficult to view within an MRI image may be missed, but the other models like brain or lungs or heart or liver, this could be very easily just put out. There are AI based algorithms which are already taking care of the demarcations, like they have done some thresholding mechanisms and coding within this. From the software standpoint, they can clearly pinpoint which is what organ, which is very cool to look at. The DICOM data from the CT or MRI images can be uploaded within this software in order to begin the segmentation process. From this data, 3 views are present: the coronal, axial or the sagittal. Another window is to present the display of the 3D objects. So, these are the 3D organs. You can then click on those organ models separately, bring this to a further analysis software or 3D print it, or whichever way you would like to use it, you know. So, just to showcase some of the outcomes of this DICOM image segmentation process. So, the first example is a dental model. So, typically you are looking at these 3 set of images, 3 set of planes which has a stack of images of its own, and you are looking at all this set of images and try to segment it through an auto segmentation, and it comes out with a very nice dental model with a clear demarcation of the basically the gum and the different teeth, right. So, this model can be readily used for so many modifications to look at surgical training, surgical simulations and 3D printing and so forth, right. So, this is the first model which is very unique. Second is the knee model, where it can be quickly developed using a mimics kind of software, where this can be thresholded, like the bone is clearly outlined and the 3D model will be out exact to the real dimensions, right. So, no scaling or upscaling or downscaling happens here. So, the other one is the hip portion. So, here you are typically looking at the different regions of the hip. So, it is not a continuous bone which is there. There are some adhesions, and of course, like things are together, it's in the form of an assembly, but you have different bony regions which are kind of demarcated here as per the image thresholding, and they are developed as separate models. Later on you can assemble them through some kind of connect based operations which you can do as a part of the simulations, right. So, another example is the heart valves. So, you can see the heart valves are not very easily demarcated by this image segmentation softwares, and the figure at the very bottom right, you can see some bubbles here which is not able to very clearly showcase the heart valve, right. So, there are some limitations with these kind of DICOM images and the image modality which we are using. So, several of the soft tissues cannot be seen very discreetly, and you may not be able to really get a model out of that. You may need a different imaging modality, like there are so many modalities like diffusion tensor imaging, right. It's a DT-MRI based imaging, and so many other techniques which can let you get a better insight into the tissues and whatnot. Along with that, if you do the image segmentation, you will get a particular design. So, with this we are going to close this session. We will continue this topic in the next lecture. So, thank you all.